Good day everyone. Today I will be presenting a research paper entitled Application of Ground Penetrating Radar and Electromagnetic Geophysical Tools and Sedimentology for the Evaluation of the Subsurface of Sites Earmarked for Aquaculture Ponds in the Amazon region of northern Brazil. Aquaculture is increasingly vital for food security and rural livelihoods, particularly in Brazil, where small-scale fish farming is expanding. However, site selection remains a critical challenge, often hindered by the high cost and inaccessibility of traditional soil assessments. To overcome this, our study explored the use of ground-penetrating radar and electromagnetic induction as non-invasive, cost-effective tools to evaluate subsurface conditions. By combining these geophysical methods with sedimentological analysis, we assessed two potential aquaculture sites in Braganca. The goal is to enable better informed decisions for pond construction, reduce environmental risk, and improve the long-term sustainability of local aquaculture efforts. In this section, I'll be presenting the materials and methods used to assess the subsurface conditions of the study sites. The researchers conducted ground-penetrating radar, electromagnetic induction, and standard penetration tests along with sedimentological analysis. These techniques provided both geophysical and geotechnical data to support site evaluation for aquaculture. This study examines two aquaculture sites in Braganca region of northern Brazil, both on flat terrain near water sources. Area 1, about 8 km from Braganca, is planned for the Northeastern Para Aquaculture Center, and Area 2 is a private fish farm in Trocotea. The region has a rainy season, which is December to May, and a dry season, which is June to November, influenced by El Niño and La Niña. As shown in Figure 1, the study area is located in the state of Pará, Brazil, highlighting the precise location of the two sites within the municipalities of Braganca and Trocotea. We applied ground-penetrating radar and electromagnetic induction to evaluate subsurface conditions. GPR uses high-frequency waves affected by soil moisture and composition to map underground layers. EMI measures soil conductivity and permeability without contact by inducing electromagnetic fields. Together, these methods provide fast, non-invasive, and reliable data for assessing aquaculture site suitability. The Standard Penetration Test or SPT is a common geotechnical method using percussion drilling with circulating water to evaluate soil properties. It measures the compactness, consistency, subsoil types, depths, and water level by dynamically driving a standard sampler into the ground and recording the penetration resistance, which is N value. This information is essential for assessing subsurface conditions and guiding construction and foundation design. At Area 1 in Braganca, GPR data were collected using a GSSI SIR 3000 system equipped with 200 and 400 MHz antennas, operating within a 200 nanosecond time window. A bistatic setup with fixed transmitter receiver spacing was used. To ensure data accuracy, we perform calibration by inserting a metal bar to a depth of 50 centimeters. All measurements were georeferenced using a handheld Garmin GPS for precise spatial positioning. As shown in Figure 3A, the geophysical profiles cover the area where the Aquaculture Research Center is under construction, while Figure 3B displays the exact locations of the excavated ponds within this site. In March 2017, detailed ground-penetrating radar surveys were conducted at both study sites to characterize subsurface conditions. At Area 1 in Braganca, 4 profiles were collected with length ranging 40 to 240 meters and sampling intervals of 5 to 10 meters. At Area 2 in Trocotea, 2 profiles measuring 400 meters and 105 meters were surveyed, both with 5-meter intervals. The image in Figure 4 illustrates Area 2, a privately owned aquaculture facility in Trocotea, where these surveys were performed to support aquaculture development. Electromagnetic induction data were acquired using the portable EM343 conductivity meter, which operates in horizontal and vertical dipole modes. The horizontal dipole surveys depths approximately 0.75 times the coil spacing, while the vertical dipole reaches about 1.5 times that distance. Coil spacing of 10, 20, and 40 meters allowed depth investigation from roughly 7.5 to 60 meters. In this study, Area 2 was surveyed using the horizontal dipole mode with 10 meter spacing, reaching depths up to 7.5 meters. These surveys were aligned with the GPR profiles for integrated subsurface analysis. To evaluate soil suitability for aquaculture ponds, we used the jar sedimentation method, which allowed us to measure the proportion of gravel, sand, silt, and clay in samples collected from 1-meter trenches. This analysis is critical as soils with at least 20% clay content are preferred to minimize seepage. In parallel, stand penetration tests were carried out following Brazilian NBR standards to determine soil resistance. The N values derived from these tests provide insight into the soil mechanical behavior, supporting decision on pond design and construction feasibility. For GPR data, we applied a series of processing steps to clean and enhance the radar grams, including filtering gain correction and background noise removal. Time depth conversion was performed using the hyperbole overlap method with a propagation velocity of 0.092 meter per nanosecond. For EMI data, we use Golden Surfer software to process conductivity measurements through spreadsheet editing, triangulation interpretation, and map generation. These processing steps allowed us to produce clear and accurate subsurface models essential for site evaluation. We will now proceed to the results and discussion section where we present the main findings from the geophysical surveys, sediment analysis, and SPT data. These results are examined to evaluate subsurface conditions and determine their suitability for aquaculture pond construction with insights drawn from the integration of all methods used. In Area 1, which is Braganca, GPR prospection using a 200 MHz antenna reaching depths of 8 to 9 meters. However, signal noise was observed below 1 meter, likely due to water saturation from seasonal rainfall. The profiles revealed an abrupt depression reaching up to 4.5 meters deep, as well as a compact surface layer between 0.25 and 0.5 meters. These key features are clearly visible in Figure 5, which presents the GPR profiles along transects AB, BC, CD, and EF. In Area 1, GPR profiles revealed several subsurface depressions, with the deepest reaching approximately 4.5 meters along line AB, and shallower features along BC, CD, and EF. The latter, situated near the Rio Grande, yellow zones on the radiograms represents areas of low reflection which likely correspond to soft or moisture-rich soils. Conductivity mapping, as shown in Figure 6, indicates values ranging 3.5 to 17 millisiemens per meter, typical of clay-rich subsoils. These elevated conductivity levels associated with yellow latosols derived from clayey and sandy clayey sediments suggest favorable condition for aquaculture pond construction due to reduced water infiltration. As shown in Figure 7, the GPR prospection in Area 2 utilized a 200 MHz antenna and 200 nanosiemens time window, achieving a depth penetration of approximately 7.5 to 8.5 meters. The profiles reveal high noise level below 1 meter, but clear horizontal layering is evident near the surface between 0 and 1 meter. The water table was identified at depths of 6 to 6.5 meters, which was later confirmed by a well drilled on the property. The GPR profile in Area 2 reveals clear horizontal layering near the surface and a water table around 5.5 to 6 meters deep. Between 1.75 and 5 meters, hyperbolic reflectors likely indicate buried pipes. Signal attenuation is shown by yellow shading on the radargram, and according to the conductivity map shown in Figure 8, Area 2 exhibits higher conductivity values than Area 1, ranging from 16 to 48 millisiemens per meter, which aligns with the clayey yellow latosol soils identified. Soil samples confirm a high clay content, particularly below 1 meter, supporting the geophysical data. Soil moisture increased electrical conductivity, limiting GPR penetration, especially in saturated clay soils. GPR effectively identified near-surface features and water table depth. Electrical conductivity was confined as a key factor in assessing soil suitability for aquaculture, while sedimentological and penetration tests supported the geophysical data confirming favorable soil condition for fish ponds. This finding guided pond construction at Area 1, demonstrating the reliability of the integrated methods despite COVID-19 delays. The study confirmed that the soil substrates in Area 1 were suitable for fish pond construction, enabling the excavation of 15 pods at Shanpa between 2020 and 2021. These ponds were designated for different uses: 12 for fish farming, 2 for wastewater treatment, and 1 as a reservoir. Despite delays caused by the COVID-19 pandemic, the project was successfully completed by December 2021. Figure 9 visually documents the aquaculture installations, the demarcated pond boundaries, and the excavated ponds, highlighting the progress and practical application of our research findings. The initial excavations confirmed the geophysical survey results, with pond depths reaching a maximum of approximately 1.6 meters as illustrated in Figure 10. In conclusion, our study demonstrates that combining ground-penetrating radar, electromagnetic induction, standard penetration tests, and sedimentological analysis provides a comprehensive and reliable method for evaluating subsurface conditions for aquaculture pond construction. This integrated approach enhances site assessment accuracy, promotes sustainable and cost-effective aquaculture practices, and can be extended to other water-related infrastructure and environmental conservation projects. That's the end of my presentation, and thank you for listening.